Hi everyone. Today we'll talk about designing different controllers, P, PI, and PD using sisotool and in particular in the frequency domain. So let's do this through a couple of examples. Imagine I have a transfer function which is of the form g of s is 10 divided by s times s plus 2, s plus 20. This is a third order transfer function, and this is my feed-forward path. And let's say the desired characteristics of the system for me are rise time of 1 second and overshoot to be less than or equal to 10%. This is what I want to achieve. And what we'll do is we'll first start with the easiest controller, which is a proportional controller, to see if there is a gain k with which I can achieve these two characteristics. Let's translate these into system parameters. So rise time, we know that rise time is 2.2 divided by omega n. If this I want it to be 1 second, that means omega n needs to be 2.2 radian per second. And then overshoot of less than 10%, that roughly translates into damping ratio being greater than or equal to 0.6. Now, last time we talked about relationship between frequency domain parameters as well as time domain parameters. And we saw that there are two important things. One is that the crossover frequency of the system, this is a frequency where the gain of the system crosses positive decibel values into negative decibel values. In other words, the frequency where the system stops amplifying the output and starts input and starts attenuating the input. So this is roughly approximated as your omega n, meaning that if you want to achieve a certain omega n, hence a certain rise time, you have to make sure that the crossover frequency of the system is that value. And also we saw that my phase margin in degrees divided by 100, that is approximated as zeta. So if I want a zeta of greater than 0.6, that means my phase margin has to be greater than 60 degrees. So what we'll do is we'll go to Matlab and we'll use the siso tool in order to design this system. So in Matlab, first you have to, of course, define S so that Matlab knows it's not just a variable, it's the variable for class. So you can, I mean, there are different ways to define S, but the one that I usually use is S is transfer function of S. And then at this point, Matlab understands that whenever you type S, you mean the variable for class. And then let's say my G, I write it as 10 divided by S times S plus 2 times S plus 20, my third order system. So now what I need to do, as before, we just type sisotool, which is siso stands for single input, single output. Then you press enter. It takes a little bit of time for Matlab to open the sisotool page. In that page, as we will see shortly, you will have different boxes that will show Bode plot, both phase and magnitude. Will show you the root locus as well as the step response of the system. So let's wait for it to come up. Once it does come up, which is now, what you have to do, of course, initially is going to be blank because no information has been, important in it. So what you have to do is you have to basically export your system from Matlab into sisotool so that sisotool starts providing the corresponding plots based on the system that you have. And yeah, like I said, it does take a little bit of time to load everything. Um, but while we're waiting for it to be loaded, let me explain to you that the one uh, particular menu option that we usually use is this edit architecture. What you do is you click on that and then you essentially import the functions that you want from the workspace, or you can import them from the math file as well. All right, so it's ready, and as you can see, it's not showing anything because it's not associated with any system. So what we do is we go to Edit Architecture, and you click on Edit Architecture, and a menu pops up that will give you different options. This is the one that we usually go with, that has a controller transfer function, a feed forward transfer function, a feedback transfer function, and a constant function that is amplifying or attenuating your input signal. If you don't change some of these functions, they're basically set to their default value of 1. So since we want a transfer function with unity feedback, I'm not going to touch anything except for G. So what you do is for G, which is this function here, you click on this button here, which is essentially allowing you to import data into sisotool. And there are different ways to do it. One is that you can import from the workspace or a math file if you have something ready. I don't have it in a math file, but I have it in my workspace. And as you can see, I have both G and S that I have defined in the workspace. So I click on G, I select that, and I say import. After I click import, I press OK. And then what sisotool does, it basically tries to load all the different characteristics of that function. So as you can see here, this is your magnitude Bode plot, this is your the phase Bode plot, this is your root locus, and your step response. So let's see what we wanted. We wanted a rise time of 1 second and overshoot of less than 10%. Overshoot is okay, but not rise time. You can come to this step response and you can actually right click and say, I want to see different system characteristics. And let's look at my rise time. And Matlab provides that, graphically, the time it takes from the output to go from 10% of its final value to 90%. And if you click on this, you will see that your rise time is 7 seconds, which is a lot slower than what you want. So let's go back to the characteristics that we found. What we said was I want my crossover frequency to be equal to my desired natural frequency, in this case being 2.2. And also my phase margin, I want it to be, so my phase margin, I want it to be around 60 degrees. I would have to play with the K value, which is the gain, in order to achieve these two objectives. So I'll go back to my sisotool. And if I want to increase the gain, K, basically, as you can imagine, that means that in decibel value, it becomes more and more positive. So one way to do this is you can grab your Bode plot, and by moving it up or down, and this is a bit tricky, yeah, you grab it, and by moving it up or down, you essentially increase or decrease your K. Notice that if I decrease my K, the system basically, manages to achieve this, 1, which is the desired output. However, it becomes a little bit oscillatory, and if I increase K, and notice what is happening here. My poles start moving towards the right half plane, so the system becomes unstable. So it's very important to choose the right K. Now, what do I want? I want my crossover frequency to be 2.2 radian per second, or around 2, and my phase margin, I want it to be 60 hertz. So let's bring this down a little, because right now my system is unstable, and if the system is unstable, none of these conversations actually make sense. So let's bring it down. Let's say I'm somewhere here as an example. So the system is stable, but again, it's not what I wanted it to be. As you can see, my frequency, my crossover frequency, which is the frequency at which the Bode plot crosses the frequency axis, goes from positive decibel to negative decibel. That's 1 radian per second. That's lower than what I want. I want it to be 2.2. My phase margin, however, is okay. So what I can do is I can increase the gain a little bit. And notice that when I increase the gain, what is happening is I'm shifting the magnitude plot upwards. When I'm shifting the magnitude plot upwards, that means the crossover frequency, the frequency where the plot crosses the omega axis, that increases as well. So I moved it up a little and noticed that my frequency, crossover frequency went up to 1.69. I need to move it a little bit up so that, and as I do this, pay attention to this crossover frequency here. It's really a little bit tricky. You have to go up and down to make sure you get to the frequency. So as I'm moving this up or down to get to exactly that 2 radian per second, there are a couple of things that I want you to pay attention to. One, notice that how the phase margin changes. Right now it's 24 degrees. And notice also, as I start increasing the gain, the system becomes more oscillatory, which is what we have talked in class, and it's something we expect. If I lower the gain, the system becomes less oscillatory and a little bit more stable with more damping. So I'm going to be trying to move this up or down in order to get to exactly 2.2 radian per second, or as close to it as possible, because right now the crossover frequency is at 3, and I want it to be at about 2.2, which is somewhere here. That means I have to move this down, and I'm going to try to do this very carefully. Look at the crossover frequency at the bottom, and 2.6, 2.19, and that's actually pretty close. So what I managed to do was I managed to bring the crossover frequency to 2.19. I wanted it to get to be 2.2, which is close enough. And let's see if my rise time is what I want it to be. It's perfect. Rise time is half a second. Is much better than what I expected it to be. I wanted it to be 1 second, and now it's half a second, which is better. You might ask yourself, so why, despite the fact that I brought that crossover frequency to 2.2, why is it that I'm not getting a 1 second rise time and I'm getting half a second? That is expected because these are all approximations. First of all, that equation 2.2 divided by omega n, which is your rise time, that's an approximation based on a second order system. This, in fact, is a third order system. Further, the approximation that your crossover frequency is the same as your natural frequency, that again is an approximation which is not 100% accurate. So what you do is you typically target a particular natural frequency, and then you say, this is what I want my crossover frequency to be. So rise time checks out. However, the other thing that I wanted to achieve was a overshoot of less than 10%, which meant I wanted my phase margin to be 60 degrees or more. This is not the case here, however. See that my phase margin is 36 degrees, which is less than what I want, less than 60 degrees. And you can actually see it in the step response as well. What you can do in order to see exactly what your overshoot is, you can right click here, go to characteristics, and look at the peak response. And Matlab shows this to you graphically. If you hover your mouse over this point, you will see that overshoot is actually 33%, which is a lot more than 10%. What this tells us is that this system, with just the P controller, with just changing the gain, is not able to achieve these two design criteria. And you should probably expect it too, because notice that I have very little, margin to play with the pole locations. If I increase the gain a little bit, the two loci corresponding to those poles, they cross into the right half plane, making the system unstable. So with just the P controller, this cannot be achieved. And this oftentimes is the case, meaning that whenever you want to design a system, you usually start with a P controller. And then if you cannot achieve your design criteria, you move on to a more advanced type of controller. So the next option that I want to try is going to be a PD controller. And this is not a kind of a, blind choice. I know that PD can make a system fast but smooth, and this is exactly what I want. Because if I just use the gain using the P controller to make the system fast, I can see that the system becomes more oscillatory. So it does become fast, but it becomes less smooth. In other words, like less, with more oscillations. What I want to do is I want to get a PD controller to help me achieve that objective. So PD controller, let's come back here. PD controller, if you remember, was in the form of, so your controller was of the form of, let's say, some KP plus a KD times S. So what it does essentially is it adds a zero to the system. And what we do whenever we want to use sisotool for this purpose is I write this or rewrite this as KD times S plus KP over KD. This is essentially the same thing. However, what I just did was the following. I looked at a PD controller and divided it into two components. I said it's going to be adding a zero and then a gain. So essentially, I'll be doing both of these at the same time. I'll add a zero and then play with the gain in order to achieve what I want to achieve. So let's do it here. This adding the zero, however, is not, again, is not a blind exercise. You have to see what you want to achieve. Let's go back to this situation I have now. The system is pretty fast, so I'm getting a rise time of less than 1 second, which is good. But it's very, very oscillatory. When it's oscillatory, that means zeta, your damping ratio, is small. Damping ratio is small, meaning that your phase margin is small. And this is exactly what I see here. I noticed that if I wanted to get a damping ratio, an overshoot of less than 10%, that meant that I would have to have a damping ratio greater than 0.6 or a phase margin of greater than 60 degrees. Here is 36 degrees. So what do I need to do? I need to use a PD. And what a PD does, PD adds a positive value to the angle. Let's look at the Bodhi plot of a zero. If you have a zero of, let's say, s plus a, you remember that a is going to be your breakpoint. So from a magnitude perspective, you have a magnitude of zero, and then you start having a magnitude change with a slope of positive 20 dB per decade. And then for your your phase angle, my breakpoints are going to be 0.1 times A and 10 times A. So I will start with an angle of 0, then a angle with a slope of plus 45 degrees per decade, and then I will settle at 90 degrees. So this slope is going to be plus 45 degrees per decade. So when I add that 0, it will basically add a positive angle to the overall angle of the system. And before we discuss these types of controllers in frequency domain, we basically covered the fact that a PD controller helps the system become faster, but at the same time, provides a smooth response, adds to the damping of the system. Now it should make sense to you, because what the PD does is, because it's like a zero, it's adding positive angle to your system. When you're adding positive angle, that means you're improving your phase margin. And phase margin is directly translated into stability of your system, or the damping level of your system. So this is why, at least in explaining through frequency domain, this is why a PD controller can help your system with achieving more stability. So what I want to do is I want to get a phase margin which is close to 60 hertz. Now this is going to be an approximate design. I'm not able to exactly get 60 degrees. But what I do is I add a zero, and I want this phase improvement to happen somewhere around this angle of this frequency of 2.2. So in order to do that, I would have to add the zero around the same frequency. In order to add a zero, you come to this plot, your root locus, you right click and you say, I want to add a pole or zero. And it gives you a bunch of options. And you come down here and you say, I want to add a real zero. Your mouse becomes active now wherever along the real axis I click this mouse, it'll add a zero there. So I want it to be close to this frequency. This frequency is about 2.2, so I will bring it close to, let's say, 2, and I click it here. Now, as I do this, I want you to pay attention to a few things. Notice how my step response will change, and notice how the phase margin will change. So I'm going to click my mouse here, and as I do, notice that it added a pole at around -6 or so, and all of a sudden my angle improved significantly. My phase margin is now around 60 degrees. So this helped me achieve both the things that I wanted. First, my crossover frequency is about 2.3, so that helps me achieve the rise time that I want, which is like 0.6 seconds now. And my angle, my phase margin here, which is this difference between the phase angle at uh, this particular crossover frequency and negative 180 degrees. That's 60 degrees, and you notice that here my overshoot is about 12%. I want it to be a little bit, more less than 12%, 10%. So what I can do is I can start moving this a little bit to the right. Again, notice that by grabbing this zero location, you can start moving it closer to the frequency 2.2. And as I'm doing this, again, notice the change in phase margin. And of course, notice that how magnitude of overshoot goes down. So I grab this zero and I move it a little bit to the right, and notice that I'm having a phase margin of 63 degrees. Let's check my overshoot. That's 8.5%, 8.6%. So that's less than 10%. And my rise time is less than 1 second. So I have achieved both the things that I wanted to achieve using this PD controller. Now I changed a lot of things, graphically by moving the zero or moving the magnitude. If at the end of the day you want to know what your controller is, you come to this section and you just click on your C, which is the controller. And Matlab gives you this controller that is 3.2 times S plus, let's say S plus 4. So if I come back here, the controller that I designed is now 3.2 times S plus 4. If I want to translate it into this format, it would be 3.2 times S plus 12.8. So that's my KP, that's my KP, and this is my S. So that's how you would design a PD controller in frequency domain. Now let's look at a different problem. So let me erase this section and consider a different problem. Here, I now have a system whose transfer function G of S is 50, S plus 1, S plus 50. This is my 50. And again, what I would like to achieve is three things. So I want my rise time to be less than 1 second. I want my overshoot to be less than 10%. And I want the steady state error to unit step to be 0. Okay. Let's translate these into what we know about frequency domain. So rise time less than 1 second, that means 2.2 divided by omega n. I want it to be less than 1. So that means omega n is going to be greater than or equal to 2.2 radian per second. Overshoot less than 10%. Again, this is corresponding to zeta being greater than 0.6. And based on the approximation that we saw earlier, that means my phase margin has to be greater than 60 degrees. And then I want the system to provide perfect tracking of a unit step input. We know that in order for a system to perfectly track unit step, it has to be of type 1 or above, meaning that it has to have one or more integrators. This system doesn't have an integrator, so that means I'm going to have to add an integrator to it. All right, let's come back to sisotool, but now I'm going to have to use a different system. So I'm going to write down this new systems transfer function, which is 50 divided by s plus 1 times s plus 50. Okay, so that's my new G. I come back here to sisotool, and what I do is I come back to edit architecture, and again I import the new G. So I on the option for G, I click on this button and I say this is my G and import. So the new value of G will be, or the new transfer function rather, will be imported, and this is the body plot and other characters. You do have to remember that in the previous example, I had already added a 0 because I wanted to design a PD control. So I'm going to have to remove that 0. So what I do is you come to the root locus plot, you right click, right under add polar 0, you go to the next option, which is delete polar 0. When you click on this, then your mouse becomes like an eraser, and you don't really need to go too close to that as long as you are, close to that value, to the 0 that you added, and you uh, press your mouse button, the 0 basically goes away. So now I have my system, which was of the form 50 divided by s plus 1 times s plus 50. All right. What I want to do, and let's look at the system a little bit first. We see that the gain margin is infinity, meaning that no value of gain can make the system unstable. This is actually what you should expect to see, right? Because notice that in my root locus, the loci, the branches will never cross the j omega axis into the right half plane. So it doesn't matter what k value I choose. I always have my poles in the left half plane. And my crossover frequency is 12 radian per second, which is a lot higher than my desired 2.2. Um, and my phase margin is 80 degrees, which is good. But right now, I'm not too much focused on that. What I'm looking into is my step response. And what do you notice here? Your final value is never going to get to 1. And if you want to be sure about that, you can right click and go to characteristics and steady state, and it shows you the steady state value. If you hover your mouse on top of this point, you will see that final value is 0.92. So your system cannot track unit step. Is this what I should expect? Absolutely, because this is a system of type 0, and we know that a system of type 0 will always have a finite yet non-zero steady state error to unit step. So what do I have to do? I would have to add an integrator in order to make sure that the system can track unit step. By looking at the magnitude body plot, you also see that you don't have an integrator. Even if I hadn't given you the transfer function, by looking at this, you would see that you start with a flat slope. And whenever you start with a flat slope, that tells you don't have an integrator. If you had an integrator, you would start with a slope of negative 20 dB per decade. If you had two integrators, you would start with negative 40 dB per decade. So first things first, I'm going to have to add an integrator. So what I'll do is I'll come here again to root locus, right click, go to add polar 0, and come to these bunch of options. And as you can see, one of them is an integrator. That's an S in your denominator. So I say add an integrator, and Matlab directly adds that integrator to your transfer function. This system, it's always good to kind of look at the response and see what you can say about it. So if I look at the body plot, the magnitude is starting with a negative slope, which is, great. That means that you have an integrator so you can track unit step. Is this what I see here? Absolutely. Hover your mouse on this point and you see that final value is 1. So perfect reference tracking for unit stuff. The problem, however, is this system is really on the verge of instability. You can see it here in the root locus because both your poles are very, very close to J omega axis. They're very close to kind of crossing J omega axis and going to the right half plane, making the system unstable. But you can also see it using Bodhi plot. Your gain margin is very, very small. It's only 11 decibels, and your phase margin is only 11 degrees. Using our approximation, this is like less than 0.1 for damping ratio, which is not good. So what I have to do is I'm going to reduce this, try to play with the gain by, grabbing the Bodhi plot for magnitude and moving it up or down to see where I can improve my transient behavior. Because notice that because of the fact that I have an integrator, my steady state performance is guaranteed. I don't have to worry about that. But I am worried about this very, very high overshoot of about 72%, as you can see here, although my rise time is pretty good. But overshoot is not good, so the system is very, very oscillatory. So what you do is, again, you grab this, and again, remember, when you grab your Bodhi plot and move it upwards, that means you're increasing the gain. When you're moving downwards, that means you're reducing the gain. So as I'm kind of playing with this, I want you to notice a few things. Notice that as I move it up, most likely this is going to be more oscillatory and at some point becomes unstable. When I move it down, it becomes less oscillatory and more stable. And then also pay attention to my phase margin. If I move this up, that means my crossover frequency will come to the right, meaning that my phase margin becomes smaller and smaller, and at some point becomes even negative, which is unstable. If I move this down, that means that my crossover frequency, again, remember crossover frequency is the frequency at which the Bodhi plot crosses the positive decibel values into negative decibel values. When I move this down, the crossover frequency becomes smaller and smaller, and phase margin becomes more. So what I want to do, just to achieve my objectives, let's remind ourselves of the objectives. I want to have a natural frequency which is approximated as the crossover frequency. So let me actually write this here as well, to be around 2.2, and then phase margin of 60 degrees. So let's come back here, and I'm going to be trying to, just for the sake of example, see that if I move it up, the system becomes more oscillatory and unstable at some point, right? So that's what I expect. The poles are in the right half plane, the output is oscillatory. So basically I want to go in the opposite direction. And what I'll do is I'll move this down until this is what I'm going to be looking at. So I want my phase margin to be, the frequency to be around 2.2 or something like that. So I'm going to be moving this down, grab it and move it down. And let's say, 1.96. I'm okay. You don't necessarily have to go exactly to 2.2. I mean, something in that range would be okay. So this is 1.96 of, crossover frequency, which is giving me a very, very good rise time of 0.6. That's perfect. I have about 25 degrees of phase margin, and about 21 decibels of gain margin. Phase margin is pretty small. I wanted it to be around 60 degrees. Now it's about 25 degrees. So that means it kind of corresponds to damping ratio of 0.25, much less than 0.6. And you can see it here because, again, your overshoot is extremely high. What that tells me is by just adding an integrator, I'm not going to be able to achieve all three objectives. I need something else to help me out. So what I need is a PI controller. So PI controller, you remember that it was of the form KP plus KI over S. So that was my PI controller. And if I combine it together, it would be like this, KPS plus KI. So what this tells me is that a PI controller has an integrator as well as a zero. I just added the integrator. All I have to do now is I have to add the zero, and then I will have my PI controller. Let's go back to sisotool. And again, before I do this, because remember that although this is a lot of trial and error involved in this process, this is not a blind process. There's a lot of logic behind it. Why am I adding a zero? Because just as I showed you in the previous example, a zero adds to the angle of the system, right? If it does add to the angle of the system, that means it improves the phase margin. That's exactly what I need. I need a phase margin of about 60 degrees. My phase margin is about 25 degrees. So I would have to have a zero around this frequency of 2 radian per second to help me increase my phase margin, get it close to 60 degrees. So what I'll do is I'll come here, right click, add polar zero, I go to real zero, and then I want to place it as close to like 0.2 as possible. So let's put it here, wherever that point is. That's actually -10. This shows you that my crossover frequency is 2 radian per second, which is giving me a good rise time. However, my phase margin is still not good. So what I have to do is I have to start moving it to the right or left to see what I get. And again, as I grab this zero and move it to the right or left, I want you to notice two things at the same time. Notice your phase margin, notice your magnitude. When the phase margin increases, the magnitude of overshoot will have to go down. And I will grab this and start moving it to the right. Take a look at my phase margin. It's now 38 degrees. And notice that the peak of overshoot is going down. Let's bring it here. And I'm at 50 degrees. Let's move it a little bit to the right. So now, this is kind of a little bit difficult to get very accurately to where you want. But now this is a lot closer to what I want than before. So now my frequency, crossover frequency is 2.5, which is greater than 2.2. That's perfectly fine. Take a look at my rise time, 0.6 seconds, less than the 1 second that I want. My steady state response is still guaranteed because I already know that I have an integrator. That's a type 1 system. It tracks unit step. And also my phase margin is 68 degrees now. I look at my overshoot, and as you can see, overshoot is 9.48, less than 10%. So all three objectives have been met this way. If you want to know what type of controller you designed, again, you come to the left side, you click on C, and this is what you have. It's 2.05 times S plus 2.1 divided by S. So if I write it here again, it's 2.05 times S plus 2.1 divided by S. I can write this as 2.05 plus 2.1 times 2.05. Let's say this is 4.3 or something like that, divided by S. So that means that this is your KP, this is your KI, and that's your PI controller. So we're going to stop here. Again, as I want you to, as you go through this, this video lecture, I want you to pay attention to a few things. Before we have done this just using root locus, and we've seen how by moving the location of the poles, we can get the desired performance in terms of transient behavior of the system. Now we're trying to kind of connect it to frequency response. So you can see that there is a duality between your omega n as well as your damping ratio, your zeta and omega n, between what you have in time domain as well as what you have in the frequency domain. So your omega n, your natural frequency, which directly determines your rise time, is approximated as the crossover frequency of the system, which is the frequency at which the magnitude becomes negative in decibels. And your damping ratio is approximated by your phase margin divided by 100 degrees. about divided by 100. So what I encourage you to do is just to, do some additional examples, choose random systems with, more or less number of poles and zeros, and then set different design criteria, and then see what kind of controller you would need in order to help you achieve those criteria.